Okay, so we're going to do a bit of scene setting here where I'm hopefully going to make a link between the constant acceleration formulae work that you did at AS and where we're going to lead it into 2 dimensions in A2. So let's just set the scene with this example here where we've got a football of mass 500 g. It's kicked so that it sets off horizontally across a flat field with a velocity of 10 meters per second. Describe what happens. So the only impetus this football is going to have is in its initial kick. After that, it's just moving under its own steam, so to speak. So following it being kicked, it's going to slow down until it comes to a rest. So slows down uniformly because the deceleration will be constant until coming to rest. That's what's going to happen. And we're given the mass and we're given an initial velocity, and the question is, what other measures could we find? Well, we could work out what that uniform slowing down is, which is known as its deceleration, or we could say acceleration, and we know when we can't calculate it, it'll work out to be negative. So we could find its deceleration, we could find how long it took before it came to rest, so the time of the journey, and we could find out how far it's travelled at the point it comes to rest. So those outcomes we could calculate using the Suvat formulae that we met at AS. What assumptions are we making in order to model this mathematically? So as you know from other work we've done in mechanics, we have to make assumptions to simplify the model. And when it comes to the movement of this ball, we are going to assume that acceleration is uniform. Uniform is just another word for constant, because we wouldn't be able to use the Suvat equations if it wasn't. The ball is modelled as a particle. That means that the size of the ball makes no difference to the calculation. It's just a point mass. So it's modelled as a particle, and it's not going to bounce, it's not going to roll, it's not going to spin. We model it as if it's being translated, it's just shifting across the surface. So no bouncing, spinning, etc. Ball comes to rest 25 seconds later. How far did the ball travel? So we're going to do some maths now. So we know that it sets off with an initial velocity of 10. So I know that u is 10. I know it comes to rest, which means I know its final velocity is 0. I know that's going to happen 25 seconds later, so it's going to be in motion for 25 seconds, and I want to find how far the ball will travel, which is s. So you've got your Suvat formulae, which you need to know, and the one that links those most easily is that one. S equals u plus vt over 2. So that for me is going to become 10 plus 0 over 2 times 25, which is 5 times 25, which is 125 meters. So that ball is going to travel 125 meters before coming to rest. What is the magnitude of the constant resistive force acting on the ball? Well, once I see the word force, I know that I need to get a Newton's second law relationship going here. So if here's my point mass, which has got a mass of 500 grams. Now I know that that's 500 grams and not 500 times 9.8 because it's telling me I'm talking about a mass. If it was 500 times 9.8, it would be a weight. So 500 grams is the mass. I need to have that in kilos in order to work with Newton's second law. So it's 0.5 of a kilogram. And I know that if it's accelerating in that direction, it's being resisted by a force opposing the direction of motion. So using Newton's second law, I know that if you think of the other Newton's second law work we've done, we take the direction of motion to be positive. So I'm going to have minus r equals 0.5 times the acceleration. And I'm trying to find that resistive force. So I need to get the acceleration from somewhere else. So I'm going to get that. I know V, U, T, and I want to find A. So 0 equals 10 plus 25A. So A will be minus 10 over 25, which is minus 0.4 meters per second squared. Put that now into equation 1. And I get minus r equals 0.5 times minus 0.4, which means r works out to be the resistive force of 0.2 newtons. So that's all AS work. So the next question that I pose is what would happen if the ball was kicked so that it sets off vertically from a point 1 meter above the ground with a velocity of 10 meters a second? So this is the other work that you covered with Suva in AS, which is vertical motion. So what would happen? Well, initially it would start to rise, and during that part of the journey it would slow down uniformly. So it would decelerate uniformly under gravity. Gravity would be trying to pull it back to Earth. And that would continue to happen until instantaneously it came to rest. Now when it comes to rest, in the previous scenario where we were moving horizontally, it would just stop. But because this comes to rest in mid-air, that's just the first part of the journey, because then the direction of motion changes and it starts to fall once more to ground. So there's more going to happen with this. So it's going to decelerate uniformly under gravity until it comes instantaneously to rest. So the phrase instantaneously there is basically saying that that's like a split second where it's not moving while it's changing its direction to start falling again. It doesn't hang in the air for a few seconds. It's an instantaneous change from upward motion to stationary to downward motion. So it comes instantaneously to rest, and that will happen at its maximum height. Once it's reached that, the height will start to fall again. So what happens then? Well, it then accelerates uniformly again under gravity. And that will continue to happen until it hits the ground, until something stops it from falling. And that, in this particular case, is going to be 1 meter below the point of direction. Point of projection. So there's a lot going on with that ball when it's moving vertically rather than horizontally. So what else could we find from the information that we're given? Well, we're given its position when it sets off. We know its initial velocity. We know its velocity when it comes instantaneously to rest, which means that we can work out its how high it reaches at that point. Okay, so we can work out its maximum height, or we can work that out from the point of projection or from the ground. Time to the maximum height, we could work that out. Time of flight. So the time of flight would be how long it took between leaving the person's boot that's giving it a kick to landing on the ground. Total distance travelled. As opposed to its displacement, which we know its displacement is going to be -1. It's going to be just 1 meter from the point of projection when it comes to a rest. And how fast it's travelling when it hits the ground, which would be the speed of impact. So plenty of things there that we can calculate, even just from what appears to be limited information we're being provided with. So as far as assumptions, it's the same ones as in the previous example, where it's going to be a point mass. It's not going to have physical size to it. But on top of that, the most important ones when things moving in the air is that there's no air resistance unless they give you it to work with. No wind that's going to change its direction. No wind. It's not going to spin, because if you think of balls spinning in the air, that again has an impact on its direction. If you think of footballers that can make a ball swerve in the air, that's a relationship between the spin they're putting on the ball and the air resistance, and we're taking both of those out. Same with a cricket ball. So how long was the ball in the air for? Well, we know it's got an initial velocity of 10, and we know that it's accelerating under gravity, which we take to be 9.8 meters per second squared unless we're told otherwise. And we know that the ground is 1 meter away from its point of projection, and we want to find its time. Now, one of the ways that I teach this when I was teaching AS was to use the arrow notation, where you put little arrows to show which direction things are initially. So it's initially being kicked up with a speed of 10, so that's got an up arrow. Gravity is opposing that, it's trying to pull it down. The distance is 1 meter below. So that's the situation that we're setting up. And then from a point of view of signs, the rule is that you turn all the arrows to point the same way before you do the maths. And the easiest thing to do there is to change that one. And if you change the direction of the arrow, you change the symbol, the polarity of it. So in my formulae now, all of those are pointing in the same direction. So I'm going to take u to be -10. So what links S, U, A and T is S equals ut plus a half at squared, where I'm trying to find out what t is. So I've got 1 equals -10t plus a half times 9.8t t squared. 4.9 t squared minus 10t minus 1 equals 0. So that gives me a quadratic equation. So just stick that on my calculator. (4.9) minus 10 minus 1, and I get t equals 2.1, and then the other value of t is negative. Because of the context of the question, I know that t is a value of time, can't be negative, so I can ignore the context. T equals minus 0.1. Can only be 2.1. And then the second, what was the maximum height of the ball? Well, we know that at max height, it's instantaneously at rest. So V equals 0. I know that U is 10 up. I know that A is 9.8 down. And I want to find S, which I don't know, but I know it's up. So this time, I'm going to change A to be minus 9.8 to get that arrow going up. So what links V, U, A, and S is this one. So 0 equals 10 squared plus 2 times minus 9.8 times S. So S is 100 over 19.6. So 5.1 meters. So it's 5.1 meters. That's above the point of projection, because that's where we were measuring things from. Question's asking for the maximum height, so that is above the ground. So we need to add another meter. So the maximum height is 6 meters, 6.1 meters above ground. So both of those scenarios, with the horizontal kicking of the ball and a vertical kicking of the ball, are all situations that you would have met back in year 12 when you were looking at SUVAT for the first time in one dimension. Where we're moving to this year is a scenario such as this. Now the ball is kicked, so it sets off horizontally from a point 1 meter above the ground with a velocity of 10 meters a second. So rather than being kicked vertically, it's now going to be kicked horizontally, which means that it is going to fall in a parabolic arc like that until it strikes the ground. And it's going to strike the ground some distance from the point of projection in a horizontal plane, and we know it's going to be 1 meter below where it started. So describing what happens, the ball is going to fall with a horizontal acceleration. Sorry, not an horizontal acceleration. There is no horizontal acceleration. The only acceleration is going to be drawing it to the ground. So it's the acceleration due to gravity. So the ball will move both horizontally and vertically downwards until striking the ground 1 meter below point of projection. And its motion is only accelerating due to gravity. So acceleration only acts in vertical plane. So what other measures could we find? Well, we could find x, its horizontal distance. At impact. Time of flight, how long it takes. Speed of impact. And these are all things that we will be performing calculations on over the next few lessons as we work through this two-dimensional motion. What assumptions are we making in order to model mathematically? Well, the assumptions are the same as they were for if it had been kicked vertically. So all the same thing. It's a point mass. There's no air resistance. There's no wind resistance. It's all happening in the same plane, etc., etc. So the points that we need to consider when dealing with a projectile that's moving in two dimensions is that we work horizontally and vertically separately, and that when we're working horizontally, the velocity is constant in that horizontal motion because there's no acceleration acting horizontally. The only acceleration is vertical. Okay, so that's the sort of preamble. Where we're going next is to start looking at some specific examples to develop our capacity to work with projectiles.